Okay. After that glitchy video, hopefully this part will go okay. So, last lecture we talked about the law of Bio Savar, and the Bio Savar law allows you to take an arbitrarily shaped current carrying wire and calculate the magnetic field that it generates as a function of position around the wire. The position is tricky because there's cross products involved, but I hope you all know now how to manipulate those. So that's not too complicated, but there is, of course, the issue with doing Biot-Savart is that it's a direct integration, just like what we had when we had when we started doing electrostatics and we had an electric field, and if we didn't have enough symmetry, we had to do this quite tedious process of direct integration, which always works. You can even do it numerically, but it's not always the fastest approach. So for that purpose, we used Gauss's law, and today we'll introduce a similar thing for magnetism. So think about a little bit about the fundamental object and a fundamental field in electrostatics. So the fundamental object is a charged object, and the field is the electric field. And the fundamental central force that connects the two is the Coulomb Force Law. So K, Q1, Q2 over R squared. And we were able to peel that apart by saying, instead of having this charge talk to this charge directly, we said, well, this charge generates an electric field. So take this charge out of the equation. This charge creates an electric field, figure out what that is, and then place that charge back into the problem. And then we had the electric field. And then the way we got from electric field to Gauss's law is we recognized that the field depends on distance as 1 over r squared. And because spheres have a surface area that is proportional to r squared, the flux is a quantity that is independent of distance, and that's how we got the Gauss's law. So it was that 1 over r squared distance dependence and the r squared distance dependence that canceled. So the thing that was doing the work was the 1 over r squared and the r squared. Now, you might be tempted to think that we could do a similar thing with Biot-Savart law, because in Biot-Savart there is a 1 over r squared, except the problem is that you can't do that, because if you want to do something similar to Gauss's law, we already know what Gauss's law is going to say for magnetic fields, because that's Maxwell number 3, Gauss's law for magnetism, that says that the flux through any Gaussian surface is 0. So you can't use that. So we need something else. So let's get back to the way that I started with electrostatics. So we need something similar as the Coulomb Force Law. So why don't we take 2 current carrying wires? So 2 really long current carrying wires, and the force between those 2 current carrying wires. And we calculated what that was, and it was actually an interesting exercise, because in that case, currents that were running in the same direction were attracted to one another. And it was a central force, so it's a nice force that is in a that is exerted in the direction of the vector that's joining the 2 objects. So could it be that we could use a current carrying wire as the fundamental physical object that we can use to construct something similar to Gauss's law, but then for magnetism? And the answer is yes. So in that case, what we're going to do is we're going to take that picture of the 2 current carrying wires, and we'll do the same thing that we did for electrostatics. We say, okay, instead of calculating that force directly between this one and that one, we're going to take one wire out of the equation. We're going to look only at this wire and the field it generates. And then afterwards, if we want to know what the force is, we just stick this wire back in. So, so therefore, we need to have a distance dependence. Well, in the case of magnetism, that distance dependence is the one that we calculated explicitly with Biot-Savart. It's magnetic field of an infinitely long current carrying wire, or a really long current carrying wire, field goes like 1 over r. All right, so that's the distance dependence that we will need. Now, we need to find some kind of a geometric object that has the opposite distance dependence, such that if we integrate something that goes like 1 over r and we integrate it over something that has a size proportional to r, then we could work with the same kind of cancellation that allowed us to get to Gauss's law, but now we'll do it for magnetism. So off the top of my head, I don't really know any other geometric object than the circumference of a circle. Circumference of a circle happens to go proportional to r as well. And now the beautiful thing is that instead of having a field that's radiating out, actually the field for magnetism, the magnetic field goes in circles around it. So that's nice. So field goes in circles. The circumference of a circle has the right r dependence, such that when we do something funny with the product of those two terms, maybe we can come to some kind of a nice, more ideal law that allows us to calculate magnetic fields a little bit easier than the quite tedious task of using Biot-Savart. So that's the plan for today. We'll develop that, and we'll do that. Another thing I want to talk about just briefly, and that is the Helmholtz Coil Setup, and we'll do that in a minute, because that's actually the magnetic field that you're using in the lab. If you're taking the 220B lab right now, that's the magnetic field that those two coils generate, and we need to know why they're set up in that manner, because it's actually rather important for that lab. And usually that lab is taught way later in the semester. It's lab 10, and we're only on lab 6 or 7. So we have to jump ahead a little bit with that, because otherwise I think some of you are going to be scratching your ear needlessly when you are confronted with the Helmholtz coils. So we'll do that. All right. So we are October 13, 2020. So I promised to talk to you about the Helmholtz coil. So we know that if we have a current carrying wire from our previous class, that this generates a magnetic field. Now, if this wire is front and this wire is in the back, that means that the magnetic field is generated in this direction. Okay, so that's the magnetic field, that's the current, and we can find that with the right-hand rule. So curve your fingers in the direction of the current. In the case, I had the current circulating in this manner, and then your thumb indicates the direction of the magnetic field. So, and we know what that field looks like because we have calculated it. And let me see if I can draw that on here. So the field is biggest here in the middle. So, and then becomes smaller. So bigger, smaller. So this is the magnitude of B plotted as a plot, on this thing. So it's not that the field lines do this, it's the magnitude of B. So field is biggest right here in the middle, and that is a diagrammatic way of notating that. So that's field number one. Now, if I take another another coil. So I'm going to take this coil, and I'm placing it exactly the same way. So that means that the current flows in the same direction. It's the same magnitude of current, and of course I didn't draw it the same size, but let's assume that I was less handicapped when drawing. So the field of this also does the same thing. So it's biggest right here in the middle, and then it decreases. Now the question is, what's happening here in the middle? Now in this case, the setup is not very good because the field's already small, and doesn't work very well. And if you want this field to be nicely homogeneous, you would like to be able to add these two magnetic fields, and there be no curvature here in the middle. So if you don't want a curvature, that means that you need to have this part be exactly linear, so no curvature here, and this part exactly linear. And when you overlap those two, you'll get a field that is nicely flat and doesn't vary much with distance. So it turns out that that is, if you do the algebra, that is exactly the case when the distance is the same as the diameter of the loop. So this is R. There you go. So that's really neat, and therefore that means that you can set up a system like this, and you have a field, a region with a field that seems to be quite uniform. So therefore you can do this experiment, putting a needle in the middle, and you don't have to worry about inhomogeneities in the field. All right. So this is known as the Helmholtz coils. Setup. And the criterion is that second derivative of B dr, so distance, sorry, dz squared is 0. So then you get a nice large region with uniform field, and that is the case when the distance equals R. So Helmholtz coils. All right. Now, to the business of today. So electrostatics versus magnetism. So in electrostatics, we have the Coulomb Force Law is K Q1 Q2 over R squared, and that's the central force that we use to start our discussion with. And then we got a field, which was the electric field, and the electric field went like 1 over R squared. And then the geometric object to integrate over was a surface of a sphere. And then we got a flux, and then we got Gauss's law. Oops. All right. So the physical quantity okay. So now in magnetism, I don't like magnetostatics as a word because it really does depend on the fact that there are currents that are flowing. So there's always something moving, but it's sometimes called magnetism. So in this case, the central force is that force that is proportional to both currents, I1, I2, and over R. And then that's for two really, really long wires. And now the field is the magnetic field, and that is, I'm sorry, this is a proportionality. The field is a magnetic field of a single wire, right? So we pull these things apart, and the field is proportional to 1 over R. And the geometric object that we're going to integrate over is the circumference of a circle, circumference circumference of the circle. Now, the physical quantity that we'll end up getting is a magnetic potential. So VB or V sub M. Magnetic potential is a weird thing because it's a scalar potential, and actually this one ends up being a little bit funny to work with. But then as a result, we'll get this thing called Ampere's law. So the law that we'll get is Ampere's law. So that's the program for today. So let's do that. So I'm going to draw a long current carrying wire and current carrying wire. And we know what the field is because we have already calculated it. So the field, if we assume that this is a infinitely long wire, we know that the field goes like 1/r, and the magnetic field lines go in circles around. So let me draw a couple of those field lines. They go in circles, but not behind a wire. Usually, if you want to indicate in a drawing that it's going behind something, you draw it like this. All right. So that's the way the B field looks. This is the current carrying wire, so that's the current, and that is the magnetic field. Okay. Now, what do we need? We need an integral over B over the circumference, and that is a line integral. So we'll do a delta V sub M for magnetic field, and we're going to define that as the line integral and B dl vector. I'm sorry, we won't use this. But we're not actually going to use this as a potential anywhere in this class other than for this particular part, because I want you to see that this is very similar to the electric potential difference, right? So an EDL and a BDL. So that's the physical quantity that we'll use, except we're not going to do this over wires that have a beginning point and an end point that are distinct. We're only going to do this over closed paths. So we'll execute this integral over closed paths, and we'll do that in a manner that is going to help us arrive at Ampere's law. So let's do the first one. So we'll do this, and we'll go over the red contour, and we'll do this over a closed path. And now we'll calculate the integral, and this is a closed integral, so that's why I'm doing this. So it's the closed integral over the edge of a circle. So BDL. All right. Now, if we choose this path in the direction of the magnetic field lines, so that means that there's a sense of direction to this integral, so like this, then we know that at every point, that B field is pointing exactly in the same direction as that DL, because a DL here, oh, sorry, pointed here. So DL vector is always tangential to that circle, so we can always use that. So if they're always pointing in the same direction, that becomes just a B times DL, and we can drop the dot products. All right, so easy enough. Now, that means we'll do B DL. And we know that the magnetic field is mu naught I over 2 pi r. And we know that that's the same field everywhere. So when we integrate that over the length, we integrate that over the length of this circle. And now that's the world's most simple integral because this thing, none of it depends on r. So we get mu naught I, right? Because the dl, when you integrate it, gives you 2 pi r. So therefore, this line integral always gives you mu naught times I. So if you want to do an explicit integral, by the way, I can write it. So for instance, you could do a mu naught I over 2 pi r, and then you could do r d phi, where you integrate with phi going from 0 to 2 pi. So if you really want to do it that way, you'll see that this r and this r cancel, and now the mu naught I over 2 pi you can pull out of your integral. All you're left with is an integral over d phi from 0 to 2 pi, and that's again the world's most simple integral. It's just 2 pi. So you get mu naught times I. Done. Okay. Now let's talk about what happens if we change this radius. Well, obviously, whenever we change the radius, as long as this path is in the direction of the magnetic field lines, then we can be sure that there will be we can be sure that there will be an outcome of this line integral that is always going to be mu naught times I. All right. So when we were doing Gauss's law, this was the point where I went from a sphere to an avocado. So we'll do something similar today. And today the food item of choice is a pizza slice with a bite taken out of it. So we'll do the same, but I'll make the path that is like this, except there's a pizza slice here, half a pizza. All right, and then we continue on this path. Okay, now the line integral of BDL over the green path is now consisting of two parts. So sorry, 3 parts. So there's a BDL, and there's let me call this number 1. Let's call this number 2, and then call this number 3, and let's call this number 3 as well, because you can already kind of see what's happening. Okay. This we're going to split into 4 integrals. So BDL over number 1 plus BDL integral number 2 plus BDL number 3. And you know what? I'm going to commit to number 4. BDL number 4. All right. Sorry, these are not integrals over closed areas. It's force of habit. This is the correct notation. So it's just a regular line integral, not a closed line integral. Okay, number 1, it's this part. So we're integrating BDL, but now instead of having phi going from 0 to 2 pi, we have phi only going from 0 to pi. So the outcome of this is going to be half of what we got before. So that's mu naught I over 2. Number 2, so number 2 is executed here, over there. Again, we're going for phi from 0 to pi instead of 0 to 2 pi. So also for this one, we're going to get half of what we had before. So we're going to get a mu naught I over 2. And now, now what do we do with number 3 and number 4? Well, number 3 and number 4, the path that we're integrating over, that path is entirely perpendicular to the magnetic field. So that dot product is going to give you a 0. So this is going to be 0 and 0. And we get a mu naught I. Same. We get the same here. Now we can make the path a little bit more interesting even. We can make it, we can add a little bit of a pizza slice here. So we make a tiny excursion here on the blue path. So the blue path follows the green path. These two paths are, again, perpendicular to the magnetic field. So the dot product will give you 0 here. And this section here is going to give you the same B times angle as you're getting here, B times angle. So even for this funny pizza with a piece sticking out, I'm not sure why somebody would eat it like that. Seems quite monstrous. But you would still find for the blue path, PDL is mu naught I. All right, so that's pretty cool. Now, of course, the final step is an arbitrary shaped path. So an arbitrarily shaped path, you can always decompose in little sections. So let me see if I can draw that. Okay, so arbitrary path. I'm officially out of colors, so I better not make any more paths. So at any point here, you can always decompose this as, if you zoom in here, something that goes radially out and something that goes in this direction. So a dr and a d phi. And in the direction of dr, this part is perpendicular to the field, so there's no contribution from here. But that part that's going in the direction of d phi is going to give you that same contribution to the line integral as a part that's further in. Okay, now so therefore, even for the PDL is mu naught times I. Okay, now that's pretty convincing, I would say. There are, I can't really think of any path that will not give you an integral that'll evaluate to mu naught times I, unless the path does not go around the current. So how does that work? Well, if you, let's say, take a path where, so I'm gonna draw those here. So got a magnetic field. So that's again our field, and we'll start with the red field, but now we're not actually going to make a full circle. We're actually going to do again our pizza slice, but now the middle is out. So by the end, when we've done this integral, we will not have actually gone around this current carrying wire. We've stayed on one side. So actually, if you look at this, there's a surface area here. Current is outside of that surface, doesn't poke a hole in the surface. So in this case, the line integral of PDL through a closed path for this one will be 0, because in this direction, it will pick up some B times the angle. This is not doing anything, but here it's going in the opposite direction from this part of the path. So whatever increase we're getting here, we're getting a decrease there. So therefore, this type of line integral is going to evaluate to 0. And we can do the same thing. We can make it arbitrarily shaped, and you would find that looking from this point, as long as there's always one part of this path that goes in this direction and the other path goes in the opposite direction, if that number is even, so in other words, one this, one that, this thing will always evaluate to 0. And the only way to get a non-zero is actually if you go in a circle, like for the red path there. So let me give you an example of a path that would give you, still give you 0, but looks a little bit different. So let me give you one like this. So and we come back here. All right, so this is still 0 because this, this, and I need to make sure that I don't mix up my directions. So whatever integral b times angle we have here, there's one exactly on the opposite side, sorry, there's one exactly on the opposite side that is going to give you exact cancellation. So you see there's 1, 2, 3, 4, 5, 6 of those wire segments if you count from here. So therefore, a path like this will evaluate to 0. And this path is canceling with this, and this is with this, and this is with this. So the whole thing comes out as 0. So BDL is 0. And here also BDL is 0. So the only thing that distinguishes a 0 integral from a non-zero integral is the fact that this path needs to go around this current carrying wire. Or if you want to look at it differently, this thing spans a surface. So there's a little surface if you think about you know, as if this is like a soapy membrane. In this case, this wire doesn't poke a hole in the membrane, whereas for all of these paths, this wire goes through that soapy membrane. So therefore, that is going to give you a non-zero current, and this is going to give you a 0 current. So finally, we are at Ampere's law. Which says that the line integral of B dl is mu naught I enclosed. And that enclosed, so that's enclosed. That enclosed plays the same role as the Q enclosed in Gauss's law. So if it's in Gauss's law, when the charge is inside our Gaussian surface, we have a non-zero flux, and in this case, if the current is enclosed by, or encircled, if you want to think about it that way, by a one of these paths, then we don't have a when it is enclosing a current, then we get mu naught I enclosed, and if not, it's just 0. So it plays the same role, and the geometric object that we integrate over is an Emperian loop, which is the edge of an Emperian circle. So the Emperian loop is the thing that we'll use, or the Emperian circle, and that plays the role as the Gaussian surface for Gauss's law. So now we have kind of put the whole thing together. We can put this to use, except I need to mention one more thing. So we skipped over one quite important part, and that's unfortunately we'll have to leave that. So we only did this for an infinitely long current carrying wire. We didn't actually consider anything that is not an infinitely long wire. So you have to trust me that this also works if the wire is not infinitely long. It's just that the math becomes quite hairy, and in fact, this is not the way you would want to do it if you want to work with paths that are current carrying paths that are different. So you'll have to do some tricky bits with vector algebra, sorry, vector calculus when you want to do that part. Okay, now we're going to put Ampere's law to work. We'll start in the same way as when we were doing Gauss's law. So even though we used a point charge to derive the general form of Gauss's law, afterwards, to just kind of get our feet wet, we decided to use Gauss's law in reverse to find out what's the electric field of a point charge. So it seems like we're working backwards, but that's okay. That's just to show that we can actually start with Gauss's law instead of having to work with point charges. So we'll do the same thing today, which means that the first thing we'll do in putting Ampere's law to work is say, okay, what does it look like if you do Ampere's law in reverse? All right, so let's put Ampere's law to work. So putting Ampere's law to work. So here we go. The first, surprise, surprise, an infinitely long current carrying wire. All right, so our VDL is mu naught, I enclosed. Task 1, choose Emperian loops. I think there's a thing if you do it like this. So choose the Emperian loops. So the central feature that you want to use with Emperian loops is that you create a loop that looks like large parts of the loop will be pointing exactly in the same direction as DL, and it could have sections where the loop is not going in the direction of DL. But now let's say that if we don't know what the magnetic field looks like, so in other words, we have no idea what kind of Emperian loop to look at, is okay, identify the symmetries. Okay, now this is where we are jumping to nearpod. So I'm doing this, identify the symmetries. So that's the assignment. All right, well, so the symmetries. We have a, in this case, we have cylindrical symmetry. What does that mean? Well, it means that any point that is up here, when we rotate the system around, could end up here. And therefore, these points should be equivalent. So anything we do over there needs to also fit with what happens here on the bottom. So the only, that's the cylindrical symmetry. We also have translational symmetry in this direction because this is an infinitely long wire. So any point that we have here, if we move the entire wire over, cannot look all of a sudden different. So drawing this is a little bit tricky. So, but I'm going to try to do this. So, what does that mean? Well, it means that the magnetic field cannot have a component that is pointing in the R direction. Why is that? Well, because if it does have a field in the magnetic field in the R direction, you can't get the path to close. So we can only have a magnetic field line in the phi direction. So we could only have a field that points in some kind of a path around it. Now the question is, why can it not be at an incline? Well, on a circle on an incline? Well, that's because we have the rotational symmetry. So if this is the plane in which the Emperian loop is spanned, then if we turn this thing around, now the plane is pointing in the opposite direction. So that's not the same situation. So the rotational symmetry rules out Emperian planes that are like this. So the only Emperian plane that we can use is this. And then once you have that, you can say, well, if the only path that we can take is an exact circular path in this direction, then that is now our Emperian loop. So we'll say it's a cylindrical symmetry. And translation. Okay, cylindrical symmetry and translation symmetry. Okay, so let's do this. We'll take this path. Okay, so these are our Emperian loops. And for that Emperian loop, we have BDL is mu naught I enclosed, which in this case is I. So this is 2 pi r b, and that is mu naught times I, because b is the same. So we get a mu naught I over 2 pi r. And that's how you do Ampere's law and get the field of a wire by working backwards. Couple of notes. How do we get the direction? So we can use the right-hand rule that we had established before, that if you put your thumb on the wire, that the then the path of the magnetic field lines needs to go in this direction. Another way to encode that is to actually say these two things are related. This sense of integration is related to the I enclosed. So sense of integration, meaning clockwise, counterclockwise, is related to the I enclosed with a right-hand rule. Okay, so what does that mean? Well, it means that as soon as we pick one type of integration, then the right-hand rule says whatever sign you're going to get is going to give you the sign of that I enclosed. So for instance, if I were to say go in a direction that is in the opposite direction, I would find a BDL that would be negative that current. So we know that that sense of integration is going to fix the direction of the current. So this is a little bit trickier about Ampere's law, because when we compare this, so let's compare that to Gauss's law. So we had a E dA is a Q enclosed over epsilon naught. So the enclosed part we have here, so we have an enclosed part, there's a mu naught, and there's an epsilon naught that plays the same role. There's a dot product, there's a symmetry. This is a closed path, this is a closed surface. So they look very, very similar, but that sense of integration is not here because we're not doing a line integral. So the only thing that you can perhaps think about is saying that the flux is pointing out. So normal pointing out of the Gaussian surface. So that you can compare with this right-hand rule. Next up, the magnetic field of a donut. All right. So I have to now draw a donut, also known as a torus. So drawing it like this. So there you go. So there's a hole, and there's a current carrying wire that goes around. So I'm going to draw this wire goes around. And we're going to assume that, oops, we're going to assume that these loops are packed very tightly around, and they're packed very, close together, such that the density is infinite, if you want. So they're really, really quite a lot of wires, and they go around like this. And we'll say that the current goes like this. So it goes like this, like this, and like this. So the situation is a donut, or if you want to be proper, you can call it a torus. And the assumption is that there are many turns of the wire around it, and that's what we'll use. Okay, now we have to think about the magnetic field that gets generated. You could use, you could do this with symmetries, but you can also kind of see what's going to happen. So we know that if we have a single one of those loops, that there is a field that is generated in this direction, right? Because one of those loops generates a field like what we were using to calculate. And because we have the rotational symmetry around, any point here could end up over there. So it makes sense to think that, well, probably the magnetic field is going to go in circles. And the magnetic field is going to go in circles, and it cannot go in ellipsoid form because of the rotational symmetry, right? So we cannot have a field line that sort of skims the surface here and then, oops, and then does this. Can't have that, because when we rotate this around, all of a sudden this lump here ends up there, and that can't be, because this torus has the rotational symmetry. So if we turn it around, it needs to look identical. So therefore, this kind of field is not allowed. And the field we will get is the field lines that are going in nice circles. And it goes like that. Okay, so we have a B, dl is mu naught I enclosed. All right. In this case, if this field here is evaluated, sorry, if this Emperian loop is evaluated on a blue path, which means it's somewhere inside the donut, so it's inside this, yeah, the meat of the donut, if you want to call it that, then this will evaluate to something that is not zero. So you will get 2 pi r times b is mu naught I enclosed. Well, what is I enclosed? Well, in this case, it is the total current, so let's call that current I, and it's the total current that pokes a hole in the soapy membrane that is spanned by this Emperian loop. So let me draw that. So this is the soapy membrane, and the question is, what is that current doing? Well, it's basically poking a hole every time one of these goes through here. We get a contribution of I. So in other words, we get N times I. So many turns, by that we mean n turns. So if you want to call this 16 turns or something, and every time that happens, there is a contribution of I. So therefore, I enclosed is n times I. All right, now we get B, mu naught n I over 2 pi r. Done. That's the field. But that's the field inside the torus, or in the donut. There are, strictly speaking, there are two more situations that we could use. The first one is easy. So for instance, if the path is here, so black path, this black Emperian loop doesn't have, see there's the area that's being spanned, there's a little soap membrane here. There's no currents poking holes in this membrane, so the black integral BDL is 0, so therefore B is 0 here. I'm drawing this as a vector. I'm writing it as a vector, so that one's easy. A little bit more complicated to see is if we were to take a stroll through this around here. Ooh. So the pink path, now in the pink path, you can see if you, I don't want to draw the membrane again because it becomes really messy, but you'll see that for every turn that this wire makes around the loop, once it goes through in the positive direction towards you, and once it goes in the other direction away from you. So therefore, there is no net current. So also, BDL is 0, so therefore B is 0. So that's quite nice. Draw this here. Okay, so that's the field of a torus. This is, by the way, is a very famous configuration. You see how nice it is that the magnetic field stays inside. So there's no field lines that are leaking out. So this is actually a really good way to build transformers. And we'll talk about transformers later because the field lines stay inside the torus. Another famous example of this being used is in a so-called tokamak or toroidal magnetic chamber, and this is one of those devices that are being built in France now, where they're trying to get sustained nuclear fusion going. And what you do is you evacuate this chamber and you run this really large current here, and then you get a magnetic field going. And then I haven't talked to you about magnetic induction yet, but the idea is that in this chamber, you put a plasma, and this field is going to hold the plasma, and you can also charge the plasma. And the idea is you make it so hot that this plasma starts to give you nuclear fusion, and then we have a really nice reactor. All right, so the question is why the field is not going outside, because we do know that for a single current carrying loop, the magnetic field goes in circles around it. Okay, now imagine if you take another wire here and you take another loop and another magnetic field goes in the same direction. So this field here gets the magnetic field that goes up in this direction due to this loop gets canceled by the field that goes in the other direction. Right? This one goes up and this one goes down. So therefore, the field cannot go out here. And that goes for all of these points. So that's why the field never makes it out. Okay, finally, the field of a solenoid. So that's number 4. Magnetic field magnetic field of a solenoid. So what do we mean by a solenoid? Well, it's a tube. Let's call it a tube. And we take a current carrying wire and we wrap it around. And we'll do the same thing. We'll make it very tightly packed. So I'm drawing this in an exaggerated manner. Okay, so this goes down, down, down. And now we're going to ask ourselves, how can we use Ampere's law for this? So we'll assume that it's infinitely large. Okay, so if it's infinitely large, that means that the magnetic field that gets generated, field lines need to be enclosed into themselves. So it's conceptually a little hard to think about. So, well, but I'll try to make it clear. So, so in this case, we have again the rotational symmetry, which means that the magnetic fields can only go in this direction, and it cannot go in a direction that is has any kind of an angle with respect to the axis of the cylinder, because otherwise, if you flip it around, you have broken the symmetry. So, because you can't close the field. So we get a magnetic field that points in this direction. So goes in this direction. So that's the field. Now, how do we make this into, how do we fit an Emperian loop? And this is where our infinite wire becomes useful. So this is our Emperian loop. Now, the Emperian loop, when you're on the inside of this solenoid, is not too hard to imagine. You just get B times whatever the length is. In this case, you're going in a direction that is perpendicular to the magnetic field. So we can shrink this wire such that it's neatly tightly wrapped around it. So in that case, here you'll be going in a direction perpendicular to the magnetic field, so that will not contribute to the integral. Now the question is, what's happening here? Well, what you need to think about is that the longer this solenoid is, the more this field is going to wrap around, and these field lines are going to go further and further and further. So if you make this really, really large, this field is going to wrap around bigger and bigger and bigger. So therefore, here, B is going to tend to 0 in the limit of the magnetic of the solenoid being really, really large. Or if you want to look at it in another way, so let's say we're going to take two of these wires, and this is the way that the magnetic field goes. And I apologize, I switch my colors sometimes. So in this case, B is green. So in this case too, when you put these things close together, these two cancel, so this field cannot escape. And it's therefore very similar to the torus. So it's actually, if you want to think about it this way, it's actually, it's a section of an infinite donut. So if there's no field on the outside of the donut, then there's also no field on the outside of the solenoid. So many different ways to say field out here is 0. So therefore, we get VDL U naught I enclosed. All right. Now we need to put some numbers. So let's call this field L. Sorry, let's call this loop of size L, and we'll get that goes to 0. So we're going to make that as small as we possibly can, so we don't have to worry about that. And we need the number of turns. So let's say that this is n. So we get a mu naught times n times I. And on the left-hand side, we get a b times L. And if we make this loop bigger, so we make L bigger, number of turns that is included, therefore that is poking holes in this soapy membrane, is going to also go up. So it makes sense to define a quantity that is n over L, where we say n over L is a number that is characteristic of the solenoid. So we get a B is mu naught I n over L, and we're going to call that mu naught I little n, where little n is n over L by definition, so turns per meter. And that's, of course, that's the field inside, and the field outside is non-existent. So let's do one more. So I'm kind of running out of paper, so I'm going to do this here. So we're going to do the magnetic field inside a wire. So what do I mean by that? Well, so inside a wire, meaning let's for once assume that wires are not infinitely thin and infinitely long. Let's treat them like actual three-dimensional objects. So let's talk about, for instance, this solenoid, but then instead of wrapping the current around it, let's just pipe all that current through it. So the current looks like the magnetic field. So we'll draw the same thing, but now we'll have the current carried through this wire, and let's call this 2R. So diameter is 2R, radius is R. And what do I mean by magnetic field inside a wire? Well, if this current is carried by this wire, it's entirely reasonable to assume that the current density is uniform. So we'll assume uniform current density. Oops. Current density. And what do I mean by uniform current density? Well, let's see. So for instance, if I imagine now I am only interested in the bottom half of this wire, and I put a little screen here and I say, okay, now imagine that I'm counting electrons or whatever the charge carriers are. How many would go through half the wire? If the current density is uniform, then this would be half the total current. And if I were to take a section on the top half, and I would say how much current goes through it, I would also get half. Or if I take an arbitrary slice dA, no matter where I put it, the current that flows through that area is going to always be that fractional part that goes through that area. So, so the total current is going to be the surface integral of J times dA, where J is the current density. And therefore we need to do it like this. And dA has a vector that is pointing in a normal in the direction of J. So total current, current density is uniform. So J uniform. So no R or phi or Z dependence. And that's what we will assume. Okay, so let's talk about the magnetic field. Well, we already know what the field looks like. We know that the field, the only type of field that is allowed in this kind of cylindrical current carrying wire situation is a field that goes in circles around. So let's draw. That's what the field looks like. Oops, goes in circles. And when we do Ampere's law outside, so an Emperian loop R greater than R, but let's not worry about exactly what happens at the perimeter, then we get the same thing that we had before. So BDL mu naught I enclosed. So therefore we get a B is mu naught I over 2 pi R. So I total current. Now what happens when we're on the inside? All right. So R less than R. So for instance, imagine that there is a Emperian loop here, and it has some kind of a surface area that is obviously smaller than the cross section of the wire. And we ask ourselves, okay, if we do an Emperian loop here, how much current goes through this soapy membrane that is spanned by this thing? Well, it's going to be whatever the current density is times the surface area of that loop. So on the inside, we have BDL is mu naught I enclosed, when an I enclosed in this case would be the surface area A times the current density J. You could write that as an integral, but integrating something that's constant would be rather silly. So in this case, this would be mu naught I times pi times R squared. And J is the current density, so that's actually the current divided by pi big R squared. So there we go. So enclosed current. And the left-hand side will still give you 2 pi b R. All right. So we get a B field. That is, let's see, so cancel this. And we get 1R. So we have a mu naught I R over 2 pi R squared. Okay, so I believe I did that right. R squared, pi R. Yep, I think I did that right. Yep. All right. Now, the final thing you want to do when you have a situation where you have one solution outside and one solution inside is you want to make sure that these B fields are going to give you the same expression when you take the limit of R going to exactly the transition between these two. So in other words, if little r is equal to big R, that means this is just mu naught I over 2 pi big R. And in this case, that would be big R, but here would be big R squared. So we would get mu naught I big R over R squared. So in other words, mu naught I over 2 pi big R. So that's nice. So the limit of, let me write that here because it's nice. So limit R B is limit R B. So we're approaching the boundary between these two from two different directions. We have two expressions for the magnetic field, but at that boundary, that is going to give you the same exact field. All right. Well, that's all I wanted to do today. So remember, Ampere's law is to Biot-Savart as Gauss's law is to direct integration with dE. And the symmetry for magnetic fields is a little bit trickier than for electric fields. But if you keep your eye on the ball, you should all be able to do it. And actually, you should also realize that just like with Gauss's law, there's really only a handful of situations that have sufficient symmetries for us to be able to actually solve the magnetic field, just like with Gauss's law. So I believe this is all of them. I'll do some more digging, but I don't think there's any more geometries that you could use. So worst comes to worst, you just memorize what it looks like. But if you are averse to memorization, realize that the symmetries actually tell you that this is the way it's supposed to look. And with that, I want to thank you all and see you on Thursday.